Hello, good morning. I thank you for your introduction. As she said, my name is Eliana Florento. I'm from Argentina. I am a professor and researcher at Good Research Laboratory from the School of Agrarian and Forestry Sciences of National University of La Plata, Argentina. Before I start, I would like to thank to the organization committee for this invitation. It's a pleasure for me to be here today. And I will try to be clear. So, to start, I'd like to point out that this presentation deals with this research published on Engineering Structure journal in 1992, but basically machine learning applied to timber grading. As you can see, this research was the result of the teamwork of a lot of people that work at the University of Valladolid as member of the Timber Structure and Wood Technology Research Group, and I speak on behalf of all of them. I share with you the GeoEI, but it's not open access. If you want it, email me and I share it with you. So, to start talking about our work, I will pose a question. How is structural soft timber grading? So, firstly, the species and provenance should be known. Then the soft timber is suspected and its defects are evaluated and measured to grade it according to the standard. In this case, we use this Spanish standard because it's the only that includes Populus spp timber, and has two grading timber class, ME1 or very good timber, and ME2 or lower quality timber or good timber. The third class is rejected or non-structural class, where the bad timber is included. Later, we assigned the strain grading, and in our case, we use the EN 338 standard. This assignment is very important because it gives us reference values without hard and expensive laboratory tests, and give a big opportunity to add values to their products. Some mills have the opportunity to add values to their products. In this picture, you can see the class of visual grading, and in this picture graph, you can see the strain classes standard. In our case, these assigned values were corroborated through physical and mechanical destructive testing, because we need to know the real values, the real strain values, and to know if the assigned values coincide with these real values. And my question is, will they really coincide? Well, to answer this question, the main aim of this paper was to evaluate the qualifying efficiency of supervised machine learning algorithms in 3 scenarios, and to compare the performance with that of the Spanish visual grading standard. In scenario number 1, the specimens were grouped using visual defect variable, that is to say that the set of input variables referred to as variable 1. In scenario number 2, other than the set of variables just mentioned, we also include cut type. That is to say radial, tangential, or mixed Sauer system, which we refer to as variable number 2. Finally, in scenario number 3, we added to the previous variables 2 non-destructive testing, which allow us to determine dynamic modulus of elasticity by ultrasound and longitudinal vibrational analysis, which we refer to variable number 3 or scenario number 3. But how did we work and what material did we use? In this case, we worked with this clone, Ospopulus euroamericana, 20 years old timber at 12% moisture content. The defects were evaluated about this EN standard, 1310, and these defects were measured with this standard. Then all the samples were classified following this Spanish standard in MP1, MP2, or rejected class, or class number 3. These were also the input variable to the scenario number 1. Additionally, all the specimens were classified by cut type in radial, tangential, and mixed Sauer system. Scenario number 1, or variable that include in scenario number 1 plus cut type, refer to a scenario number 2. Then, all of the specimens were evaluated through non-destructive testing. In this case, we use FACUP, a microsecond timer, and to determine ultrasound wave velocity, and FFT analyzer to determine vibrational frequency. In both cases, the dynamic modulus of elasticity was determined. These variables, together, scenario variables to a scenario number 2, were considered a scenario number 3. But also, we need to know the real values of these specimens. And so that we carry out static bending, to determine modulus of elasticity, modulus of rupture, and density. Then, these parameters were considered as values, characteristic values, that is to say mean of modulus of elasticity and 5 percentile of modulus of elasticity and modulus of rupture. We use these parameters or these characteristic values because they are the most important parameters used to characterize this material. For statistical analysis, we work with our software with different packages and libraries that I mentioned mention just a few here. The assumption of independence, normality, and homoscedasticity of the density, modulus of rupture and modulus of elasticity data were checked for all groups. In this graph represents this analysis. For cross-validation, we work with 945 Populus I2013 beams and with respective real strength values. As you can see in the graph, 155 beams were classified was C18 class. 415 beings were classified within the range C14 and C18, and 337 were classified below C14 class. Out of the total number of samples, 80% were used that data training classifier, and 20% were used as data testing. To validate the model prediction ability, 10 fold cross validation were used, and with 5 repeated time. A final model classifier was developed using 9 different algorithms in 3 scenarios. These algorithms are shown in this table, and to evaluate classifying performance, we use multi-class confusion matrix. In this graph, you can see the general confusion matrix, and in another graph, you can see a specific confusion matrix for each class. Class 1, class 2, class 3. Here I highlight the matrix of this confusion matrix. To evaluate the classifying performance, we use different global metrics. These global metrics highlighted with red color are the most important that we use. Also, we use metric by class, with sensitivity, specificity, and precision by class were the most important ones that we use. Now, let's move on the results. And in this graph, you can see that the better parameter was obtained in ME1 in the higher class, visual class, but the mean of the modulus of elasticity did not comply with the requirement of EN338, because the modulus of elasticity required for this standard is 9,000 MPa, and this value is lower than that. This cross indicate no compliance of with statistical assumption. Also, when we analyze the sample through confusion magic, we saw that accuracy and non-information rate were too low. That is to say, the level of accuracy of the non-information rate was higher than with the other classifying method, like blindfold classification. And if I analyze this magic, we can see matches undergrading class or undergrading values that imply economical problems and overgrading values that imply a structural risk. As regards metric by class, we can see that we have tried, we can see that the percentage of class number 3 or reject class is the most matches values. To improve that, we work with algorithm in the 3 scenarios. The scenario number 1 use the same variables used in visual grading. In this slide, you can see the confusion matrix of scenario number 1 and visual grading, and if I analyze the improvement of algorithm, you can see in this, for example, in this parameter, in accuracy parameter, where with this scenario we could improve. In this figure, I want to show all of the algorithm, and you can see the scenario number 1 is the word, and scenario number 1 is the color violet. It's the word, but it was better than the visual grading alone. Visual grading is remarked here, or highlight here. Scenario number 1 is which consider only visual grading, and it's the least predictive of the real class of the whole scenario. When we add non-destructive variables in scenario number 2, we can see that this prediction improved in all of these global metrics, and for all of 9 algorithms. When we test, for example, in the random forest, we found that the real values comply with the strength values required by EN 338 standard, and the accuracy improved from 50% approximately to 16% in the scenario number 1, with respect to scenario number 3, that is the scenario that includes non-destructive testing. As shown in this figure, the relative importance analysis corroborate the influence of the influence and improve of timber grading through the inclusion of non-destructive testing. In this case, we represent non-destructive testing are represented by V18 and V17 variables. And in scenario number 1 and in scenario number 2, the most relative importance of variable was face, node size, slope of grain, and ring Y. But although the cut type didn't or was only slightly influential variable, it significantly improves accuracy in scenario number two, and scenario number 3. Cut type in this case are represented by the 15 variable. So, as conclusion, we observe a poor qualifying efficiency of this Spanish visual grading for Populus, for this clone of Populus euroamericana structural timber, with matches in reject class and with high percentage of under and overgrading, which imply big problems. For example, undergrading makes for the sale of good timber at a lower price, and overgrading offers higher strain values than the timber can actually offer, and therefore there is a structural risk. Also, we found that C18 class for ME1 visual grade did not comply with the minimum standard values. These values should be C16 class, not C18. In all scenarios, supervised machine learning improves the classifying performance with respect to visual grading, and non-destructive testing and cut type incorporation were better predictors than defects alone. This is why we consider that supervised machine learning could be an efficient and cost-effective tool to implement in the timber grading process. That is all for me. Thank you for your attention. I hope I've been clear enough. If you have any question, I am happy to answer them. Thank you.